Hi, everyone, and thank you for joining. Hopefully, more people. There was quite a bit of registration for this lecture and event, and hopefully more people will join as we go along. But we're going to start in time, as we always do. I want to first make sure that you guys can hear me. So if you can hear me, please raise a thumb up or a hand or something like that. Okay, great. Thank you, Spencer. Thank you, guys. Thank you, Maria. Thank you, Joshua. Now, before we start, there is a Q&A session. You guys can use it to ask questions along the lecture. And this lecture is, let's make it as informal as possible in terms of questions. Feel free to ask questions in the Q&A section. I will try to monitor it as we go along and respond. Jevden, my partner for this lecture, Dr. Jevden, will take the second half of this lecture and we'll dive in the wireless communication problem and how we can use important sampling there. And while I'm going with the introductions and the introduction to important sampling in Monte Carlo, Jevdan, I would appreciate if you can monitor the Q&A section and let me know if there are questions. I will do the same when you're talking. Okay, now I'm going to share my screen. Okay, let's start this. Okay, great. Okay. So we accidentally started in the last slide here. Let's present. Okay. All right, so welcome to the guest lecture, Important Sampling in Wireless Communication. This lecture explores the advanced technique of important sampling. It's a powerful Monte Carlo method to enhance efficiency of simulations. Of Monte Carlo simulations, we will learn the fundamentals of Monte Carlo simulations, challenges with rare events, and the principles of important sampling, and how it can reduce simulation time and computational requirements, as well as the variance, while maintaining high accuracy. A little bit about the speaker. You probably know me, either from Cal Poly Pomona, I'm a professor there, or from my company Aleph Zero, or from LinkedIn. My guest lecturer and my partner for this lecture is Dr. Jevdan Kapenovic. He's a principal engineer at Huawei R&D Sweden. He's an expert in signal processing, communication, information theory, and programming. He's experienced in setting up simulators for communication standards and applying machine learning for wireless communication and statistical method for wireless communications. Okay, let's start with Monte Carlo and important sampling. What are these? So important sampling is a technique used in Monte Carlo simulations to efficiently estimate properties and characteristics of rare events. This lecture will explore a little bit about the theory behind Monte Carlo simulations and then behind important sampling. I will show some Python code to demonstrate it, and we'll cover key concepts like importance distributions, likelihood ratios, the weights of the importance sampling method, and so on and so forth. This will take about 20 minutes. The first 20 minutes, I will take them, and then Jevdan will take the other 30 to 40 minutes, and we'll dive into the work with communication, wireless communication, and important sampling, and you guys can see how it all ties up. Okay, so a little bit about me. You know me already, so I'm going to skip that for the sake of time here. And if you guys don't know me, this is how you can reach me. Okay? This is my email, and this is my website, drnirregev.com. Okay, Monte Carlo. What is Monte Carlo simulation? Monte Carlo is a technique used to estimate probability of different outcomes. So let's say I'm tossing a coin, and we know that the probability of getting heads, if it's a fair coin, it's 1/2. If I simulate it, I will, let's say, toss 1,000,000 coins in a computer simulation, and then I will count or sum how many coins landed on heads. And I want to get at least half, exactly, sorry, not at least, exactly, like close to exactly half of the events there on heads. Okay, this is the gist of Monte Carlo simulation, and it's heavily used in many applications in many areas of science, like radar and lidar modeling, which is my field, and I'm using it all the time over there. Communication system modeling, which is Jevden field, and he will talk about that later on. Business and finance, estimating risks, predicting weather, modeling the behavior of subatomic particles, games of chance, and so on and so forth. By the way, this is a quote from my book, Understanding Probability with Python. And let me read it. In the Grand Casino of Monte Carlo, this is actually a casino, fortunes are won and lost on the roll of the dice. In the grand world of science, our world, Monte Carlo simulations unveil the secrets of the universe, one random number at a time. So you guys can get my book in my website if you want. The idea behind Monte Carlo is that we want to model complex systems with a random variables that we generate in a computer simulation. And by running a large number of trials, Monte Carlo simulations can provide probability distribution of possible outcomes. And more importantly, other than probability distribution itself, by way of a histogram or estimation, we can actually estimate a function of the random variable, for example, the variance of the random variable, which is x minus mu to the power of 2. And we can, for example, estimate the mean, which is the sample mean or the average. And by way of taking averages, we can sample moments of and other functions of random variables. Okay, the theory behind importance sampling. Before we go there, let me go here in my book. Again, in my book, Understanding Probability with Python, there is a chapter 9 on Monte Carlo simulations. And here I justify why Monte Carlo works. I give some examples. For example, if you want to estimate the number pi, we can generate a lot of uniform random variables between 0 and 1 in a square that is x between 0 and 1 and y between 0 and 1, and count the number of points that falls around inside the circle. And evidently, or coincidentally, the number of points inside the circle divided by the number of simulation times 4 is the estimation for the number pi. Okay, another example will be that. Another example will be the Monty Hall problem. If you guys are familiar with the Monty Hall problem, we have 3 doors, and you're in a game facing 3 doors. Behind one door is the car. Behind the other door, 2 doors, there are goats. After you select the door, the host, who knows what's behind them, open another door and revealing a goat. Now you're given a choice: stick with the initial pick or switch to another unopened door. What would you do? So the intuition, a lot of people say it's still 50-50, but it's not the correct answer. Okay, your chances, if you switch to another unopened door, your chances increase by 33% or 1/3, from 1/3 to 2/3. So you increase your chance, and by doing it many times, like over a lot of samples, we can simulate that in a Monte Carlo fashion, and we can actually see if it's actually 2/3 or it's 1/2, like our intuition say. And we will see if we run this code in Python, we will see that it's actually 2/3. So what we're doing here, we're actually taking 100,000 trials. That's the Monte Carlo number of iterations, and we draw a car position, and then we imitate, so to speak, the model of this game. And once we run the model of this game enough times, we can aggregate these probabilities and try to calculate them very accurately. Okay, let's go back to the slides. So what is the importance sampling? Sometimes, if we want, let's say, to sample or estimate an expectation of a function, f of x, for example, the first moment, f of x equals x, and we're estimating the expectation of x, okay, over a probability distribution p of x. This is what we want to estimate in a Monte Carlo simulation. F of x, can be x squared, can be x to the third, and can be any function of x, okay? There are some characteristics of this function that we want, but in general, let's say it's any function of x. Direct Monte Carlo sampling may be inefficient or infeasible if p of x is either difficult to sample from, or f of x is 0 for most values of x. And by difficult to sample from, let's say that we are sampling from a model that has a communication model that has a bit error rate of 10 to the minus 10, then we know that we have to run a lot, like at least 10 to the power of 10 or 11 samples in order to get just one error, right? And that will take a lot of time. That's hard to sample from. And importance sampling is a way, it's not just a lot of time, it's also it's also not accurate. The sampling is not accurate because we need more samples than just one, and we don't have it. So importance sampling is a method to deal with these kind of situations. How does it work? It's actually a trick, a mathematical trick. And let's present the trick. We define an importance distribution Q of x. It's a new probability distribution that is easier to sample from, and has a high probability of generating samples in a region that f of x is non-zero, but has low probability in generating sampling from. So the method is as such. The expectation over the function p, the PDF p of f of x, is the integral of f of x, p of x dx. And we can multiply and divide by q of x without ruining this integral. And we avoid the region in which q of x is 0, obviously, because we can't divide by 0. But other than that, it's perfectly legal to do that. And so we can formalize this by taking the expectation, instead of with respect to the PDFP, with respect to the new PDF, the importance distribution Q. But for which function? F of x times P of x divided by Q of x. And this is also called, this ratio is also called the importance weight, or the likelihood ratio, sometimes it's called. So how do we estimate it in a Monte Carlo situation? Obviously, we're not going to evaluate the integrals. We're going to evaluate the sample means over functions. And this is how we do it. We divide by n, and we just sum everything in order to get the estimated quantity of this expectation. And that this is how we estimate expectations. And this Q of x, this ratio, is also called sometimes a bias correction. It's correct for the bias introduced by sampling from Q of x instead of sampling from P of x. Okay, let's see an example of a Python script. So in my website, in the Circuit of Knowledge section here, it's actually a paid section. It's $10 a month. It has hundreds of tutorials, not only in statistics. And there is also a tutorial here under probability theory, a tutorial called importance sampling that I published quite a few months ago. And this is just a summary of what we went over right now. And here you can see that we can generate, for example, we want to estimate probability of rare event. Okay, it can be a bit error rate or any other rare event. Okay, in what we will see today in this lecture, it will be a bit error rate. So that's why I a little bit modulated it for this lecture, but it can be any rare event. And we want to estimate it, the true error is 10 to the minus 7. and we don't want to run 10 to the power of 8 samples or iterations. We want to run, let's say, 100,000. Okay? So we can introduce another probability, okay, in which the Q, the probability of error in the importance distribution will be 0.1. And then we can sample from this distribution, and we can calculate the weights. And again, it's P over Q, right? In where is 1 and where there is not an error, it's 1 minus P over 1 minus Q. That's the Bernoulli distribution, right? And then we can estimate, which is the sum over the number of samples. But the sum is not only over the samples now, it's the samples times the weights, like we saw in the formula here. Okay? So we are just basically executing this procedure. And we can see that the estimated bit error rate with only 100,000 samples, we get the 10 to the minus 7, up to a certain accuracy, which is not right now the topic of this demo. Okay, so back to the slides. This is going through what we're doing. We're introducing another importance distribution Q, and we use it to calculate weights, and then we estimate according to the formula with the weights, we estimate the new probability. Okay, it's given here in this slide. Okay, another, so the key idea behind importance sampling is that increased rare event probability. We are basically taking rare events, and by choosing appropriate importance probability, we make them less rare. And then we can actually estimate the quantities we want more accurately, which means decreasing the variance. And this is why also importance sampling is called a variance reduction technique. Okay, how do we select this importance distribution? We select a distribution that is first easy to sample from, and second will increase our accuracy of estimation, and third we'll do it in less time and less samples. Okay, what is increasing the accuracy is minimizing the variance of the estimator. Okay, in estimation theory, accuracy is 1 over approximately the variance. Okay, so sorry, it's the variance. So the variance is smaller, we get better accuracy. So how do we actually find it? You will see in Jevden's lecture, they actually found it for pretty complex cases in communication theory. And there are advanced importance sampling techniques that I'm not going to go over right now, and applications, rare event simulation, reliability analysis, financial risk assessment, using in radar when we don't have a lot of samples. For example, if we're running a CFAR detection on further objects and the SNR is decreased, we don't have a lot of threshold crossing, but we still want to estimate that it's rare event. Okay, in communication, wireless communication, if the probability of error, of bit error, is very low, we have to simulate that somehow, and so on. The tail probability calculation. This presentation is running through the examples in my website. There is another example here, how we can shift the Gaussian to be centered around the tail of another Gaussian in order to and propose that as the Q of X, and see how we estimate the probability of a tail, let's say 5 sigma, away from the mean with just 10,000 samples. So we can do that, and we can say that the estimated tail probability is 2.84, 10 to the minus 7, and the true probability is 2.86, 10 to the minus 7, and that is with only 10,000 samples, okay, instead of 10 to the power of 8 samples, at least. All right, and there is another demo or an example there with an exponential distribution. I'm going to run over it. If you guys want, you can go from my website into my website and take a look. And I want to just conclude this quick one and hand it over to Jevden. So conclusion and future direction. Importance sampling is a very powerful technique, and it's a valuable tool for estimating properties of rare events, especially, and difficult to sample from distributions. The practical applications is radar, LiDAR, It's even used in AI and machine learning all the time, where they train neural network. They choose they want to decrease the amount of training or time of training. So they want to focus on examples that make more sense to the result of the neural network, or to the performance of the neural network. They do it by a way of importance sampling. There are a lot of work in these areas as well. I'm going to cover some of them in the next coming episodes of my 6-minute paper podcast. And there is an ongoing research like Jevdan is doing with his research group. All right. So with that note, thank you for listening for this short tutorial and presentation. And I'm going to hand it over to my partner for this lecture, Jevdan.
Thanks a lot, Nir. It was a great introduction. You covered the most important aspects of importance sampling from our perspective in wireless. So it was really, really good. As a lot of your content actually on your website. It's really things that people deal with in the industry, I have to say.
Yeah, I agree.
At least in wireless, that's what I can testify about. So, all right. So that was really good. And as you mentioned, like I saw a paper recently, they are applying it to speed up stochastic gradient descent. So they choose, the distribution in each time so that the gradient converges faster. It's a really nice work as well.
Yeah.
All right, that's going to be a great lecture. So let me share my screen then, and let me introduce what we have done.
Jevdan, can you introduce yourself as well, please?
Sure, definitely. I'm going to do that. Start screen. Yeah, all right. Can you see my screen, everybody, or?
Yes, you can see your screen.
That's great. All right, so I work as a principal researcher in the algorithm team. So I work for Huawei HiSilicon. We are dealing with the phones, actually with the terminals, so with Huawei phones. And we are looking at transmission and receiver algorithms in the phones. So we're trying to optimize those. So we have an algorithm team and a standardization team so I'm based in Sweden, by the way, in a city called Lund. It has a historically strong university in wireless communications. And so Huawei has an office here, along with Ericsson as well, and Sony and other big wireless companies. So then I conduct research on the algorithms, mostly on the physical layer. Okay, so it's very much on receiver algorithms like MIMO, beamforming as well, transmission and receive beamforming, and detection. Okay, so that's basically my background, and I have a PhD as Nir in this field from Lund University. And okay, so you can find more information about me as well on LinkedIn. And if there's anything more you want to ask later, we can of course discuss. Right. So I thought I could now start. Is there something else I should say here, or?
Yeah, no. Can you just hide this Teams bar in the bottom of your screen?
Oh,
Press
okay.
the hide
Yeah.
button.
I see.
Thank you.
All right, that's great. Okay, so then you can ask me and stop me if you want any time during the presentation. If something's unclear, we can discuss the concept. All right, so I'm going to present here a review of the master thesis we did in 2022 with this title here, and it was together with Lund University. So I supervised 2 students with a professor in coding theory on this topic of importance sampling. Okay, so here's the background of how this all started. So it was a request from our standards team in the Huawei HiSilicon department. Okay, so they want to speed up simulations of ultra reliable low latency communication systems. What characterizes these systems is that errors occur extremely rarely, like 1 in a few billion of errors. So simulations can take weeks to run. As Nir also mentioned, when you want to simulate very low errors, Monte Carlo takes a lot of time. So then they wanted to explore importance sampling. We started a research project where we looked at a simple coded system across a AWGN channel. So we're not going to go into coding here, but we're going to discuss these different channels because we use them in the thesis as well. So this research project got good results. Actually, we managed to speed up the Monte Carlo simulations a lot by introducing important sampling PDFs in a clever way. But as soon as they introduced fading, so they changed the AWGN channel to a fading channel. Soon I'm going to explain what this means. Everything just collapsed. The simulations ran as slow as Monte Carlo. Okay? So even though they used these important sampling PDFs that they proposed, as soon as fading was introduced and you didn't do anything about it, everything just collapsed. Okay, so we're going to see examples of this in the presentation as well. So fading turned out to be a big problem for this internal research project, and that's why this thesis was started, to try to speed up simulations across fading channels. Okay. So a primer on wireless channels here, I think maybe many of you are familiar with this. If not, this is a fast introduction. So the AWGN channel is very simple. Okay, you have a received complex symbol R at the receiver, say the phone, okay, which is just a sample of a continuous waveform. And then it can be expressed for an AWGN channel as the transmitted symbol, complex symbol X plus complex noise. So here, X is in practice taken as a point from a rectangular grid of points. So here we have 16 points, as you can see. So we take one of them. Let's say you want to transmit 1 followed by 3 zeros. Okay, so we have 4 bits, so we have 16 points. So you want to convey 1, 0, 0, 0 to the receiver. So you choose this point. And since the bits in practice are random, X also is random with some probability mass function, PMF. Okay. Then you have noise and added here, and you receive your R. And the noise is typically modeled actually at the receiver, and it's a pretty accurate model often, as a 2-dimensional joint Gaussian distribution across the complex plane. Okay, that's why it's called additive Gaussian noise, and white means that it's independent from sample to sample. All right, so the quality of this channel, the link quality, is dictated by the signal to noise ratio, which means it is the average transmit power of X divided by the average transmit power of the noise. So the stronger the signal to noise ratio, the less errors you're going to commit. The stronger the signal is and the weaker the noise is, right? So in order to minimize the probability of making a simple error, we apply the maximum likelihood receiver. So in this case, it's very simple because the noise is additive Gaussian. So you just look for the symbol that is closest to R. Or in other words, you look for the region, symbol region that R belongs to, where the symbol region is simply the points in the complex plane closest to a certain symbol. So here you see R belongs to this symbol region. Well, then it's going to be this symbol, the green one here, that's the decoded one. So in this case, we make an error. Okay. So this is the AWGN. What is fading? Yeah, by the way, also I can note here that, so what we're going to call everything outside of this yellow region is going to be the error region. Okay, so our transmitted X belongs to this yellow region. So it is his decoding region. So everything outside this yellow one is the error region. So in this case, the gray area here is a part of the error region. And the error region is everything outside of this yellow region, right? Okay, so that's just terminology. All right, so the fading channel is very simple as well. Instead of just the one here, you add another complex random variable, H. So you have multiplicative disturbance of the signal, not only additive. And typically the magnitude of H is smaller than 1, which means that that's where the name comes from. So the X is fading away at the receiver. And typically you estimate this H in practice, okay? In a phone, you estimate this H. So we are going to assume a very good estimator here to make our life easier in this thesis. So we assume perfect knowledge of H at the receiver. And then the ML receiver is very simple. You just divide away H. And again, you are back with the Gaussian channel. And then you look for, again, the closest point. All right. So we want to simulate the error probability, as Nir pointed out, of these type of channels. So actually, the error probability, we can write it in this simple mathematical expression here as a summation across all your signals X, transmitted symbols as we saw. So you take the probability of X, multiply with the probability of error for this x, which you call PE of x. So this is an integral because, as we saw, our received symbols are across the complex planes that are continuous. And there are two terms here in the integral that are characterizing it, right? It is what we call the channeling communication theory. It's this conditional probability. So you transmit x and you receive a certain vector r, okay? So in the case of a fading channel, as we saw here, this vector would be this non-bold r, the received symbol, and h, because we know h. So these two would constitute this vector here, r. And this is then part of the detector of the receiver to decode, right? So this is the probability of receiving a certain set of parameters r, given input x to the channel. And then this is the error indicator function, okay, to count our errors. So if the receiver is in error, it means that we're in the error region, right, as we saw earlier. Then this is a 1, it's an error. More mathematically correct, it should be a Dirac because it's an integral, but we don't need to go into these mathematical technicalities here. It's just for the sake of presentation. Otherwise, it is 0, okay, if it's not an error. So this is great, if I could compute this integral, then I'm done. But of course, this is where the issue is. Computing this integral for complicated systems, you can't do it. So what we do is, as Nir explained, you run the Monte Carlo simulation, which is basically an approximation of this PE error. Right? So we take random samples of our symbols drawn from this distribution of P, and we observe samples of the parameter vector R, taken then from this distribution, the channel distribution. This is simulation. So then the question is, how accurate is this if I have n samples, 10,000 samples, and I run my receiver and I count the errors here, okay? How do I know this is accurate? In other words, you then ask the question, if I repeat the simulation over and over again, how much does the result change? That's the variance that Nir also pointed out. So a Monte Carlo simulation, a single one, is then a realization of a random variable because it changes every time. Every time you run your simulation, you get a new value. So it's basically a random variable, and you take realizations of this random variable. And this is the random variable that we are discussing about. It is simply you take the same sum, but now you replace each realization that we have here with a random variable. And they are independent. And every time you run a simulation, you'd get a realization of these random variables. Okay, so a single simulation of Monte Carlo is a realization of this random variable, which we can call the estimator of our PE. Okay, so here we have n samples. Okay, now because this is a random variable, we can study its stochastic properties. We can actually deduce its distribution exactly, because this one here, the indicator function, the error indicator function, it is Bernoulli distributed because you're in error probability with PE, you're in error with probability PE, and 1 minus PE, you're not in error. So you know this, okay? So then the sum here is a binomial, which means we know its mean value. It's equal to the true value PE that we want to compute. So it means that if I would run these simulations over and over again, and then I take the average, I get the PE, okay? So it's unbiased. And the variance, you can actually compute it in closed form of the Monte Carlo as this. So the variance reduces with n, which means that the more and more samples I have in my simulation, the less the simulations will vary. Every time I repeat the simulation, I'm going to get roughly the same value because the variance is small of each of the simulations. But as you can see, the variance also reduces with PE. When you simulate very small error probabilities, naturally you're going to have small variations because the probabilities are also small. So what we're more interested in is the precision. Okay, so we want to remove the effect of the PE and say for any PE, how good is my precision? How good is my variance compared to the value that I want to estimate? So you take the square root of the variance, which is deviation, and you divide by the mean, which is P in this case. So you get this approximate expression for the precision eta here. And then you ask, okay, for a fixed precision eta, somebody gives me a precision. I want a simulation, a simulator that runs with this precision. How many samples do I need to take? Well, this is the answer, of the order of 1 over PE for a given precision. And this is this common saying that you need order of 1 over P samples to obtain significance in your simulation. And as we said, for urLLC systems, PE can be very, very, very low. So you need millions and millions of samples. All right. And then comes important sampling, and Nier introduced it in a very nice way. So you have already seen this. This is our PE that we just saw. In order to keep the same PE, very simple mathematical trick, multiply and divide by a certain G that you want to propose. Okay. So now, just as with the Monte Carlo estimator, we have an important sampling estimator, very similar to the Monte Carlo one, which only included this indicator function, as we saw. Now you have these weights here. So this is also Monte Carlo simulation, because it's, again, you take n samples and you sum them up, but now you have these weights multiplying your error. Again, it's unbiased. The variance you cannot obtain in a very simple closed form as before in terms of PE, because it depends on the weights that you propose, on the G that you propose, right? But as Nier pointed out, there is an optimal distribution here. You can derive it. How can we do this? Well, we reason, okay, we say, I want the optimal distribution, which means that the variance should be the same. The variance should be 0. So each simulation should give the same result. No variance. That means this random variable here, which is our important sampling estimator, has to be constant. How do we achieve constant? Well, we take G to be equal to F times this indicator function. That's where you get this term here. But since this needs to be a probability, you need to divide by the integral of this. And this is exactly our PE of X that we want to compute. So in practice, you can't compute this because you want to compute PE of X. That's why you're conducting simulation. But it does provide insight. If you look at this expression, think about it, it tells us that a good proposal PDF should behave in this way. It should be your original PDF that you have, your channel, but then it is truncated so that it's only active on the error region. And it is 0 outside. So it should be a truncated distribution of your original channel distribution. Okay, and we're going to use this observation later to introduce a very powerful method for AWG in channels, and this is going to bring great results to our thesis. So before this method, people were doing like this. So for across an AWG in channel, they introduced the following important sampling techniques. Okay, so this is the AWG channel. This is the distribution of the noise. Okay, and X, as we saw, is taken from some rectangular grid. So people typically took, okay, this N that we just saw here, and then they say, okay, I'm going to use another noise here, noise hat, N hat. I multiply my original noise with a factor beta, making it stronger, more powerful than this noise here. So N hat has more variance than N. Then this is your proposal PDF. These are the weights you get. Another way to make the noise stronger is to translate it, the mean. So you do mean translation. This is your PDF. These are the weights. So here are the results that you would get in this case. So here's a singularity probability. So now we're taking 64 points instead of 16 that we saw earlier. Okay, and you run a simulation. So here, these asterisks here, they are the theoretical correct values. You can actually compute it in closed form. The blue line here is the Monte Carlo. And I think the students of the thesis, they ran around 100,000 samples. So N was this, capital N was 100,000 in this case. So they could run the Monte Carlo down to, say, 10 to the power of -7 here, 20 dB SNR. But if you now do these techniques, you see we can continue much longer without any fluctuations in our simulation. It's still accurate. It follows a nice curve here. And this is then reflected in the precision, as we just saw. It means it's a low precision. Okay. And another interesting thing that another interesting measure is to compute the ratio of the variance of the Monte Carlo and your important sampling technique. And this gives you the speed up factor, because as we saw, the variance of the Monte Carlo can be reduced by increasing n, right? So this then tells you, okay, how much do I need to decrease n to achieve the same variance as my importance sampling estimator? Okay. So we see here, if the importance sampling estimator is mean translation, okay, the speed up factor is, 15 or 17,000, okay, compared to Monte Carlo. So it is 17,000 more samples times more samples you need of Monte Carlo to achieve the same variance as the mean translation. And variance scaling is roughly also only a few thousands here. Okay. So these are massive speedups. So things run thousands of times faster than Monte Carlo just by doing this simple technique. Okay. This is where things stood still until 2019, where two mathematicians introduced this method. They were inspired by this optimum PDF that we saw, okay? You should always make an error, basically. This is what this means. Try to always make an error across the AWGN channel. So they do this. This is their proposal PDF, okay? So they try to approximate this optimum one with asterisks with this one, okay? And they do it in such a way that it's easy to generate the values R for this one. Okay, so it is a summation across several truncated Gaussians. So the rationale is like this. Say this is your constellation. Okay, so it's like we have 6 hyperplanes that we saw with the rectangular one. We had 4 hyperplanes separating each point, right? And everything outside of this area means you're in error. So they try to generate points always outside of this area. As you can see here, all these blue, black points, they're outside of this symbol area here. So you're always in error. And they do it in a simple way. They first choose a hyperplane here, which, distinguishes one error region, this plane half space up here. And then they generate an error if that one was chosen. So they choose each half space, each hyperplane with this probability of alpha k. And then you generate an error across that plane, which is this value here. So, and this is a truncated Gaussian distribution on this, across this half plane, okay, in this half space. So every time you simulate, you choose a half space with a certain error probability, and you generate a truncated Gaussian there. Okay, so every sample here is an error. And in their paper, they show how you can do this easily, actually. It's not very, it doesn't take much to get a sample across a half space. Okay. And then you can actually compute the weights in closed form for this method. Also a nice thing. And they're equal this term here. And this is simply the error across one hyperplane, the probability of being across one hyperplane. And you have kx hyperplanes for a point x. And this value down here is only 1 or 2 for QAM. So it doesn't vary much. So these weights, they don't vary much, which causes low variance of this proposal, ALOE. Okay. And look at these speedups. So we're going to compare now ALOE. Again, 64 QAM. Let's look at this second column here. 64 QAM that we just saw earlier, where we look at the variance scaling and MT. Compare with ALOE. So we have speedups of thousands and hundreds, thousands, millions, billions of times faster compared to the variance scaling, which was thousands of times faster than Monte Carlo. So these are massive, massive, massive speedups with this method. So I thought here, by the way, I can also realize that I should have maybe already here in my previous slide show you some code on how to actually simulate this. So I prepared some code for variance scaling. Okay, so Nir has already introduced some code in a very nice way, but I thought I can do the same thing here very, very fast. So we're going to show how to do variance scaling simulation here across the AWGN channel. So can you see my Python code? Everybody?
Yeah, we can see it.
All right, that's great. So here is basically my AWGN simulation. So I'm going to take this 64 QAM. I'm going to take 10,000 samples. So this is my M. So in each simulation, I'm going to take 10,000 samples. And I'm going to have 5 different simulations just to show you that each simulation, varies. And then the variance across those simulations is what we're interested in, this precision as well. Okay, so here I go through different SNR values here. I go from 4 to 24, and with a step size of 4 in dB. And for each SNR, I make a number of simulations, 5 of them, right? That's it. And in each simulation, I simulate my AWGN with 10,000 samples. Okay, this is what I input here. All right, and then I go here, and this is how you would do it. So the AWGN is simulated by you run through all your samples, 10,000. We're going to take 10,000 realizations of our quant symbols. This is the quant constellation here. I take a random point there, so it's going to be any of these 64 random points. I generate my Gaussian noise here, every sample. It's independent. I add them, and then this is my ML detector. Look for the closest symbol and check if it was the same symbol. And this is your Monte Carlo simulation. And then if there was an error, you just say, okay, it was an error, so I count an error as 1. Okay? But with importance sampling, okay, it's very similar. It's just that instead of adding a 1 in the end, you add your weight. And it is this weight here that exactly the same weight that we have here. It is beta squared times this. And this beta, I compute in an efficient way. I took it from a PhD thesis, okay, that focused on how to compute this beta for Gaussian channels. And they found a very nice beta, a very efficient one. And it's this one here. So I compute it here, okay. And then this is how I compute my weight. It's this beta. And now this is the noise I'm using, right? It's the original noise that I have from the Monte Carlo, but now I multiply with this beta, just as you saw in my presentation here, this one here, right? And then you need to compute these weights and multiply. If there's an error, now you add W. This is interesting. And that's it. Okay, so this is how you do it. So we can actually run this code like this. So now it's computing 4 dB, 8, 12. Yeah, it's going to go up to 24 here. So it's going to be finished in 2 simulations here, all right? So, and I'm plotting directly simple rate. So you can see here, the Monte Carlo fails already here with 10,000 samples only. In the presentation, we could continue longer because they use more samples than 10,000. I think they use 100,000. While our variance scaling method can continue for a longer time. And I saved the simulation results. So let's say you take the first simulation, or you take the first, in this case, the SNR is the second index. So let's say, 0, 1, 2, 3. So around 3, that's where the Monte Carlo is gonna become bad, right? So look at how these 5 simulations vary here, okay? So this is how they vary. But if you look at the variance scaling, so each one of these value, right? It's the estimated error probability in each simulation. So 10,000 samples used for each one of these. And now if we go to variance scaling, as you can see, the variance is much, much smaller. It's roughly exactly, the same value here. Here you see they vary in the 4th decimal by 8, 6, and 3, and 2. Here, there is very little variation in the 4th decimal. Okay, this is to show this one. And then if we go to the higher one here, 4, again, very small variation for variance scaling, and Monte Carlo completely fails. It just gives you zeros. Okay. All right. So now you have a rough, and as Neeraj said, you can take a look in his website, and you're going to find all these his scripts, and I can, of course, give him mine later on, so you can go through this. All right. So now you had a glimpse of how you would do it in a simulation, wireless. So now this was a great method that was introduced for the AWGN channel that we saw. All right. It's called at least one error, allowing. massive speedups as we just saw. So let us now apply this on the fading channel that we introduced earlier, okay? So now, as we said, the PDF of our channel, communication channel, is now, because we're observing both R and H at the receiver, and we assume perfect knowledge of H and R. So we factorize this channel PDF into this way here, right? And then we have a proposal PDF, which can also be factorized. This is just Bayes' theorem, okay, as you can see. And we do the same for both proposal and our true channel PDF. And in communications, the H channel is independent from X. So this one is just doesn't depend on X, all right? So it's replaced by this FH. So now the observation is that this is an AWGN channel, okay? Because once H is fixed, once X is fixed, this R only varies with the noise. So this is a Gaussian distribution. This is like a AWGN channel. And we saw that Aloe was powerful for AWGN channels. So we're gonna say, let's take our proposal PDF to be Aloe. And we're not gonna touch the channel PDF at all. We're just gonna keep it as it is. Somebody gives us a channel PDF, we just run it, okay? We don't change it at all. We're only gonna change the noise PDF with Aloe. We run our simulation, and lo and behold, the Aloe is as bad as Monte Carlo if this H is distributed as a Gaussian, which is known as Rayleigh fading. So when H is distributed as a Gaussian as well, we have nothing. It's as we didn't do anything. All this effort we did for Aloe worth nothing. And we were shocked because we thought Aloe is so powerful. We just apply it across the fading channel by changing the noise distribution here. We're gonna see massive gains, nothing. And we were shocked. Then we need to understand why. Let's take a look at our importance sampling estimator again. So this is our proposal PDF here. It's this numerator here. Sorry, this is our original PDF, and this denominator is our proposal PDF. So what we're doing now is that when we take this GH of X to be equal to FH, right? So this term disappears. And for Aloe, you can compute this whole thing here because it makes an error every time. You can actually compute it to be in closed form to be this value. Okay. This is number of hyperplanes for a symbol. So this doesn't change too much. This, as we saw, is 1 or 2 only for a POM. This is the Gaussian Q function, which depends on the channelization, H. So when the channel varies, this Q varies between 0 and 1, which are massive variations. You go from 0 and 1, and the ratio of these two can go to infinity. So there are massive variations in the Aloe if you completely take away this effect of the channel. So you are at the mercy of the realizations of the channel. Okay. We realized, okay, we must do something about the channel. So we must use a different GH here of X. We cannot just put it to be equal to the same probability that is given to us. And again, we're going to assume that, okay, the channel should be dependent of X. So we're going to stick to this property here, okay, so that we always can generate channel independent of our transmit signal X. Before we went there, we needed to know the state of the art, okay? So what was state of the art for fading channels? Well, for Rayleigh fading channels, there was a method proposed again in a PhD thesis. They said, okay, this is the original fading channel, multiplied now again with a beta, just like with variance scaling for noise. You multiply with a beta. And they computed this beta in the thesis to, this would be a good value. This is the minimum distance of your POM constellation. And this is your SNR of the link. Okay. So it's not so strange because typically when you have a large SNR, you will not cause errors. But in this case, you want to cause many errors. So the B should then go to 0 with SNR. So that's why it has this inverse SNR relationship. Because when the SNR becomes strong, your beta should become very low, so you cause still more and more errors. And look at the performance. It's amazing. Okay, it completely removes any simulation issues with the Monte Carlo across the Rayleigh fading channel. And our Aloe was as bad as Monte Carlo. So this was amazing. We were amazed. Isn't this good enough, you might say? Well, yes, but we wanted to know, can we do much better? Is this the end of the story? It's always good to know the limits here. And also, we see it only works for Rayleigh fading. So we want the great performance for any fading distribution. So even here, I can show very fast how this would work in a simulation. Okay, so here is the fading channel now. Very similar setup as before. We again have our 5 simulations that we're going to run, 5 different simulations, 10,000 samples per simulation, 64 QAM. The SNR is going to range, it's going to be higher SNR because the fading channel is more complex. You make more and more errors. Again, very similar setup as before. And now we simulate fading here. We go down to simulate fading. So now we generate, so this is our Monte Carlo simulation here, how you would do it classically in a typical wireless communications course at any university roughly in the world. This is what they will teach you. You take your, again, 64 QAM symbol, you generate your Gaussian noise, you generate your, in this case, Rayleigh fading, so it's also distributed in a Gaussian manner. And this is your fading channel. You divide H, and you check which is the closest QAM symbol to this one, and I get its index, and then I compare these indexes, and I register if there's an error or not. So we're now going to use this beta that was given by this thesis, 6 divided by this one here. Okay, for some reason, maybe I think there should be 6 divided by 8. Yeah, there is a 0.5 here as well. So that's why. So if you multiply by 2 here, you have 8, 6. Okay, so there's, I put the 0.5 down here. Okay. And then this is the beta, it's the square root of this beta squared. So we're going to multiply our H with the beta, and you compute the weights, right? Just as here. Yeah, I didn't have the weight computation here, but this would be the weights. Okay, you compute them. And then just as before, now you're using this channel, which is the original channel H that we had, but multiply with this beta that was given by this PG thesis here. And then you take away now HIS, you look for the closest symbol and you register error. And if there's an error, you add this weight instead. So the function that Near also introduced, this f of x, is now our error function, which is 1. So you multiply it with the weight, so you get the weight here. Okay, always like that in wireless communications. When you measure errors, now you just add the weight instead. And then again, we can run this and fading. So it's going to run also pretty quickly. So I'm running 5 simulations, each simulation with 10,000 samples. So just as before, we're going to get a curve, but it's not going to go very low here. It's a tougher channel as well. We need to go to much higher SNRs, much better link quality to get low errors for the fading channel. All right, so we go down here. Again, we see the same story. Monte Carlo fails already here, and this state-of-the-art method goes here. So this is great, right? It works. Very simple. Okay. So then, what can we do? We want something even better than this. Okay, as good as possible and work for any fading distribution, because in practice, Rayleigh fading is not occurring that often. Okay, many simulations in the standards 5G, 6G standard in the future, they're not going to be Rayleigh. They're going to be much more complex. So we realized, okay, we need to do something else together with LOE. And as we saw, we need to change the proposal PDF for the channel. So again, we go back to our weights that we had. Okay, these are the weights for the LOE. When you use LOE for the noise, right, the additive noise, then you get this weight. And now this G here, we chose it before to be equal to F, right? But now we will not do that. Now we're going to choose an H or a G that minimizes the variance of these weights across all X and H. So you take an expected value of the square of this variance, and you integrate. Sorry, that's an integral, and across this, and you integrate across the GH. So you realize this becomes an integral, which is a function of your G. So it's a linear functional, and you can apply more advanced techniques such as variational calculus to optimize, to find the G that minimizes the variance of these weights. And we did that. And you can see this in the, you get this optimum solution. G should be looking like this. And it's interesting because if you remember, the optimum G is, okay, it should be truncated. Here it's really truncated, but this is kind of like the error because this T in the other way. Okay, so this is actually the optimum channel PDF of our way. Okay, but now how do we sample from this? So you give me this complicated function here. How can I get samples? And there are two ways one can continue from here. One is very interesting, specifically for our result here, and it's known as rejection sampling. Look it up on Wikipedia, for example. There's a very nice article about it. I really recommend it highly. It's a nice technique to obtain samples from a certain distribution that you're interested in. So you have samples from one distribution, you want samples from, let's say, this G, and you have samples from F. How can I get samples from G if I have samples from F? It's a very interesting technique. I highly recommend this reading about it. So basically, in a nutshell, rejection sampling works if you know this ratio, okay? And look here in our case, G is equal to this. So when you take this ratio, F disappears. And this we know. It's the Q of our channel realization and the mean. This, all of this we know, because this is the variance of our noise. This is the channel realization we have. So this is amazing, especially for us, because this tells us that we don't even need to know F. You just give me samples of F. As long as this is known, which it always is in our case, because this F is always divided out, I can generate samples from our optimum distribution for the channel. Note that if our optimization problem that we did here with variational calculus gave something that's F times F squared, okay, then this wouldn't work for unknown F, right? Because then you would need to know F in order to compute this ratio. But we were so fortunate that it was a F only appearing here as a term. So for any unknown channel distribution, we can still obtain samples from the optimum distribution in our case. Another method is Kullback-Leibler divergence. So because rejection sampling, if you read about it, you're going to see it can take time to get these samples. So we say, okay, if we know F, can we speed it up? And then yes, we can approximate then this optimum G that we have, because we know then how this looks mathematically with another function, which we guess, and it has a certain some parameters that we want to find. Okay, how do we find these parameters? Well, we minimize the Kullback-Leibler divergence between our G and the speed that we're proposing. So for example, if F is Rayleigh, you can show that actually this product is roughly Rayleigh-like. So then a good approximation here would be to choose this P as a Rayleigh with the parameter theta. And it works very well, as we're going to see. These are the simulations we got with this method. Okay, so once we're done with all the math, optimization, everything, we ran it and we were really amazed. So if you remember, this is VS Rayleigh, which was amazing compared to Monte Carlo process 64 quantum Rayleigh channel. Look at our method. We have like 60, 70 speed up at these SNRs. So simulation that would take 2 months can now take a day across the same channel. All right, 60 times faster. Now, the same thing for the KLD, which shows you that this approximative method also works perfectly. We can basically get the optimum PDF for the Rayleigh here. And now, which is really good, we ran everything across a completely different channel, not Rayleigh. So this VS Rayleigh completely fails. The state of the art doesn't work here. So then you can only run your Monte Carlo. And it's really bad, as you can see, for the number of samples. I think they chose here only 10,000 samplers or so, maybe, yeah, 50. You see, it already stops in 10 to the power of above 10 to the power of -3. You get very unreliable results with the Monte Carlo, even 10 to the power of -2. Well, our method can go as down as much as you like almost. It's quite amazing. We have very good accuracy here. And it's also reflected in precision. Look at this. Our precision is roughly 0 compared to this one. I mean, these are massive speedups. We cannot even compute the ratio here. Okay. Then you can repeat the same story across an OFDM channel, which is something that whole 5G, 4G standards and 6G most certainly will be built on. It's the OFDM signaling. I'm not going to go too much into this, but then it's not just a single scalar fading. You have a vector of fadings. Okay, so this is a vector of those H that you saw before, each one different. So it's a vector of random variables. Then you take a FFT of that vector, multiply your symbols with the samples of the FFT, and that's what you observe. So the kth sample here that you would observe, Y, would be the kth FFT of this vector times your 64-count symbol, okay, on the subcarrier K, we call it subcarrier, and then plus parity white Gaussian noise. Okay, so this is how many subcarriers you would have. So again, we repeat the same story. We did it in the thesis. Now, because we're measuring the sum of all errors across all these realizations here, the subcarriers, so we want to minimize the variance of the sum of all the weights. Okay. Repeat the same story as before. Variational calculus applied. You get this complicated function which solves a problem. Again, we can apply rejection sampling. Why? Because this always gets divided away in our case, and we know this. We can compute it for every H. Also, KLD works very well in this case, and we can show for Gaussian distributed H. Again, you can run beta, where beta is obtained as for scalar fading. Again, massive speedups. Look at this. For Rayleigh channel here, we have now speedups of thousands, because it's a vector channel. It varies much more in its probability. So now we can have thousands of speedups compared to the VS Rayleigh. So even more. And then not to mention that we can even do this across Reichenbach fading, any kind of fading. Okay. So to conclude, this thesis derived novel PDFs, proposal PDFs, IS-PDFs of the channel and the noise that significantly reduced the symbol array simulation time for fading channels. So we basically made a LOE, which was introduced in 2019 only for Gaussian channels, AWGN, to work for fading channels by further optimizing the channel PDF. And as we saw, it was enormous improvements over state of the art. And we saw that we can apply it to complicated fading distributions as well. And as well as unknown fading distributions. Please note this as well, with rejection sampling. So take-home message, final message here I want to give. Design, as Nir mentioned, design of important sampling PDFs is an honor, because you need to propose this PDF. And as we saw, computing the optimum is not possible, but you can use it as a guideline on how to propose good PDFs, as we saw with the LOE. So you use your system, your knowledge of the system, how it behaves, as a guide for proposing good PDFs. And we saw that for simpler systems such as AWGN and even the Rayleigh, even the fading channel, almost optimal PDFs could be found with our methods. So next time you simulate, as I showed with the Python script, try it out. Just scale down, for example, the fading a bit. And remember to always multiply with the weights that you compute. Okay? So that was everything I had. I hope it was...
Yeah, this was great. Thank you, Jevdan. Appreciate it very much. Do you have any questions? If so, that's a good time to start writing them down. All right, no questions. So thank you again, Jevdan. I appreciate your time and effort into this presentation. It was a great presentation. I really enjoyed it. This topic is something that I investigated investigated quite a bit in the past. We have a question here. 1 second, let me go there. In the chat, actually. Let's see. Okay.
Very good question.
Can you comment on the impact of memory in the channel?
Very good question. And to be honest, this is exactly something we also looked into internally, because I think you're aware, many of these simulators that we have in wireless are very complex. The receiver is very complex, and it naturally has memory because you do filtering across time and frequency, say, and then there is naturally memory introduced into your detector. So the errors typically get, they change with time, right? You have more data, you make less error. Very good question, and I did some work on this. I cannot share, it's a very internal work, but just as some info, which I think is known everywhere, I mean, you can, we were looking at, okay, what if the process is not ergodic? Well, in this case, it is ergodic, it's still, it's only that we have some memory, and you can deal with the memory. You just need to split things up a little bit. Things become, say, iterative. So you can still apply importance sampling across a memory channel, which is still ergodic. So you still go through all your samples. Yeah, but you need to do it in a more clever way. So the answer is yes. You can, at least from what I could see, you can still handle memory. But I would say that the weights will vary typically more. They will vary more because it becomes more multiplicative in its nature. The weights will start to multiply themselves if you have memory. And then there will be more variation introduced. So there are people looking at this now internally. I don't know all the details, but at least this is from what I could see. It's a very good observation here that, yes, memory would cause more issues, and you need to deal with this carefully. Yeah. Yeah, that's a very good point.
Right. Yeah. Thank you. Thank you. All right, guys. So thanks everyone for coming in and being a part of this lecture. Appreciate your time. Jevdan, again, thank you for joining me on this lecture. It was great.
And let's great.
Yeah. Yeah, let me have also the presentation in the code so I can post it and yes, send the emails to the participant where they can take a look at the. All right. So thank you, guys. I'm going to conclude this session now, and have a nice rest of the day and have a nice weekend. Bye bye.
Thank you. Thank you, Nir. Bye.